In this video, we're going to now apply energy ideas along with, we do different forces which will include gravity, spring, and a bunch of different things, friction, to figure out the speeds or compression and all those things. So we look at a few different situations. Let's look at a simple problem first, and let us look at two things that we could do with this problem. So let's say that we have a spring, and we have in fact two springs. Okay, let's say that the spring constant for the first one is 20 newtons per meter, and for the second one is say 10 newtons per meter. And let us say we take a block, a 10 kg block, and we compress, not 10 kg, let's take a 100 gram block, and we compress the spring. So we've taken the spring and we've compressed it by an amount, say 0.1 meter. And what we're going to do is we're going to compress the spring, we're going to let go. And when we let go, this mass is going to shoot out. So we've compressed the spring by 0.1 meter, which means energy is stored in the spring. We let go of the spring, and which means that the mass is now going to shoot out. So first question is, find speed with which the block leaves spring 1. So that's the first question. And then what we're going to do is we'll figure out the maximum compression of spring 2. Second question will be, find max compression of spring 2, the one to the right hand side. And we'll assume that all contacts are frictionless. So everything is frictionless. The mass goes straight from spring 1 to spring 2 without any friction. If there was friction, we'd account for friction. But let's not worry about friction. Let's look at this problem where we have a block that compresses the left spring, and when we let go, it shoots this block, and then it goes and compresses the right spring. So, since there are no frictional forces, we're going to use MEI equals MEF. The problem is very simple once we do this. So to use MEI equals MEF, what we're going to do is we are going to first figure out MEI for the block spring system. Once again, what we have is we have kinetic energy of the block plus potential energy of the block and potential energy of the spring. So we have KE plus PE for the block, so KEI, PEI for the block, plus PEI for the spring. So that's all we have for the spring, nothing else. In the beginning, the block is not moving, so its kinetic energy is 0. Gravitational potential energy of the block is also 0 because it's simply moving horizontally. There's no change in height. Life is good. Potential energy of the spring is 1/2 times 20 times 0.1 square, which happens to be 10 times 0.01, which is equal to 0.1 joules. Alright, we know the initial mechanical energy. The final mechanical energy is once again equal to KE plus PE final for the block plus PE final for the spring. Now, once the block has left the spring has returned to its original length, and that means it has no more potential energy. So we can put a 0 for the spring. The kinetic energy of the block is going to be 1/2 times 0.1 times VF squared, and the block obviously has no potential energy due to gravity. Alright, we have all our components. So what we know is 1/2 times 0.1 times VF squared is equal to 0.1 joules. So VF squared is equal to 2, and so this gives us VF is equal to square root of 2 meters per second. This takes care of part 1 of the problem. In part 2 of the problem, or part B of the problem, what we're going to do is, once again, we're going to use MEI equals MEF and figure out the spring compression. Now, in this case, the block is moving in the beginning and the spring is uncompressed. So we have 1/2 times 0.1 times square root 2 square, because that's the speed with which the block is moving, plus 0 for potential for the block, plus 0 for potential for the spring. Now, when the spring is completely compressed, at its maximum compression, the block is no longer moving. So it has no speed. Once again, no potential. And now all the energy has gone into the spring. So it is 1/2 times 20 times x squared that we're going to find out. So what we have is we have 1/2 times 0.1 times 2. Okay, square root of 2 square is 2. And this is equal to 1/2 times 20 times x squared. And the 2 cancels out. We have 0.1 over 20 equals x squared. This happens to be what? So it will be 0.0 x squared. And so x is equal to square root of 0.005 meters. This is the amount that the spring compresses by. In this problem, we've used the spring energy along with mechanical energy conservation ideas, and we've obtained all this. Alright, that is it for this problem.